正在录制此会议。
Okay, so even I try to stop the record, but the file size seems to be still larger and cannot be uploaded online anyway. So I will try to fix it. So we talk about that if you have the initial bending, especially we have different methods to semiconductor work function. The question is that we want to have the flat band initially in order to apply different voltage, and then talk about how do we increase the inversion layer. So for instance, for these schemes that we initially have the band structure along the surface of insulator. And then later on, we applied additional flat band voltage, in which we call it VFB. So this flat band voltage will be positive if you applied with the metal work function, which is larger than the semiconductor work function. And vice versa, if you have the semiconductor work function, which is initially larger than the metal work function. So what happened here is that we should apply the electric field from right to left. That means you get the higher voltage along the semiconductor part. So after applying this voltage, you can see we lift up the Fermi levels from the work function from metal to insulator. So you can see a split of the Fermi level with the Q phi m minus Q phi s. If you denote the number or scale of the flat band voltage, do we get VFB equals to minus of phi s minus phi m. So you can clearly see that the phi ms is determined by how much actual difference between the work function of metal and the semiconductor. And also, once you apply this voltage, you can clearly see that it could be pretty clear. It is closer to the previous case in which we have an ideal phi m equals to phi s. So under this ideal case, you can have a flat band construction, and also we do not have any accumulations along the surface of insulator and the metal. Similar things happens to the flat band voltage after you applied for the practical case in which we have the phi s, which is larger than phi n. So names at the thermal equilibriums, we get the same Fermi level, and the names we can also see the quasi Fermi level of the doping concentration is slightly higher in the p-type system. Is lower than the intrinsic layer of the p-type semiconductor. Okay, so depending on what is the initial condition, so if you get a phi n, no matter it is larger or smaller than the phi s, the work function in semiconductor, we can use the flat band voltage to tune it back. But you need to notice that the initial Fermi levels may split away from each other at the thermal equilibrium. So under the constant, you may identify it pretty close to the Fermi level in the p-n junction. Okay, so let us talk about if you apply this additional voltage from flat bands to additional band structure. So let us go back to the previous case. If you have the initial metal layer or the metal work function, the same with the semiconductor work function. And then we apply the voltage, which is positive voltage here. So what we mentioned here is that we can induce the electric field in between the insulator and also the semiconductor, and then there will be a trapped charge along the surface of a semiconductor or insulator. And then this charge will induce additional surface potential, and we label this surface potential as phi surface. Okay. And then this whole concentration in p-type regions is determined previously with P equals to Ni multiplied with exponential the difference between Fermi level and the intrinsic level. So if you consider the Fermi level is exactly in the middle of the band gap, that will give you Ni, or P equals to Ni, suggesting you get a really low concentration of the free carrier. However, if you have a high doping of a p-type semiconductors, the Fermi level will further go down close to the Fermi valence bands of this semiconductor region. You get a large difference between EI minus EF. It suggests that you get a large difference here, and you get more population in the whole concentration. And then since we get the whole concentration occupied in the p-type semiconductor, but if you go through the surface, you may notice the band structures will go down and you get an accumulation. First, deplete the p-type system and later accumulate more electrons within the surface. So under that constants, you may notice that the Fermi level may change from initially below the intrinsic layer, but later on the same with the intrinsic layer. And if you get more voltage on the metal part, you get the Fermi level, which is much higher than the intrinsic layer. So you can change the carrier, as we previously mentioned, we change the carrier type from hole to electron. So under those constants, this whole change, then we can build up a inverse operation for the MIS system. So here are some mentions of this band structure. So we get the surface in which we get the flat band condition. If you have the surface potential which is less than 0, it indicates it band should be band up at the surface with hole accumulation. Sorry, I have a typo here. It should be band up at the surface with hole accumulation. So if you get the surface potential which is first larger than 0, so you get back to the previous slide as we defined, the phi should be positive if it bend down. So if the bend down potential is close to the difference or phi f we defined here, that means you deplete the carrier. So for instance, deplete the whole from p-type to intrinsic layer. So if you get the positive one, we first go into the depletion region. However, if your surface potential is larger than 5, this means your bending is more than 5, you get more accumulations of the electron minority carrier. You can try to build up, bend down the surface below the Fermi level, and the inversion is obtained. So you can construct that initially along the surface of the semiconductor, you get the hole, just like the doping, the same doping with the p-type semiconductor. But later on, we applied the positive surface potential, bend the structure down, and we approach to the Fermi level, and the Fermi level still be like a C level, and which is flat. And then we get a strong inversion. So we get the N-type inversion along the surface is as strong as the P-type substrate. So how do we define it is strong inversion? So we define it, initially we have the P-type doping. The Fermi level is down the intrinsic layer by Q5. But later on, if you apply the for strong voltage, you get this band larger, equals to the with the same 5 but with the opposite side. That means you inverse. For instance, you assume the doping of p-type is 10 to 17, and the data with these strong inversions, we get the electron with doping as 10 to 17. You get a similar 5 after inversion. So we can define the inversion of phi surface equals to 2 times of 5. You bend it down further with 2 times of 5. So you can think that back to this slide. The Q phi, the phi surface equals to 2 times of 5. So it indicating the same potential difference between Fermi level and the intrinsic level, but with the opposite side. So under the constant, you can first define what is phi. Phi is determined by the doping concentration. As we mentioned here, phi is the difference between EF and EI. And what is the EF and EI? Let us assume it is fully ionized. So the P, the freely movable hole, is the doping concentration, is the p-type doping concentration. So Na equals to Ni multiplied with phi f over kT. So under this constants, we can replace the phi f with log Na over Ni multiplied with kT over Q. And these two indicating the factor of 2 phi f. So we can determine what is the strong inversion under the inversion operation. Let us consider, since we talk about the metal insulator semiconductor as a variable capacitor, as we mentioned, they have different operation scheme. if you first with the depletion regimes in which we get a reverse BIOS and for P-type semiconductor, we get a whole accumulation along the surface. So you get the whole modulations of the depletion region, but you get a certain capacitance. But the data is if you use different potential, you try to deplete the whole first and accumulate the electron, they will change the capacitance because you get this carrier in depletion region. So let us talk about how much space charge we can have. And wait for a second.
正在录制此会议。
Okay, so let's consider start the accumulations and the different inversion there. So first, if you apply the voltage in which we get a start from flat band condition, and of course this flat band condition is assumes that we may have additional voltage or external voltage applied to MIC system. We first assume the band is always flat. So under this constant, if you get a different work function, you get a split of the Fermi level between metal and the semiconductor. And after the flat band conditions, we try to add additional voltage. So if you are working with accumulation, that means you get more hole accumulating along the surface of semiconductor. So you get the charge accumulation around here, and you get the bending of the surface potential. You get an extra surface potential. You bend the structure. And this one is typically proportional to how much charge you accumulate. And you take the capacitance by determines the dq over dv, the potential we applied. So how much potential we apply to the service or phi service will be dependent on how much charge we get along the surface. So you can think that along the flat band conditions, it could be pretty linear. That means your capacity should be a constant. However, if you work on the other way, so first we have accumulation, but later times we deplete the potential using the inverse one. So we get a positive surface potential defined by deplete p-type material. So the band will bend down along the surface. You get the least charge along here. And then later on, you get the flat band condition first, and you can see that the charge goes down. So the slope along this region, it means you get the least depletion, you get a depletion region, you get the surface potential close to the intrinsic level. That means you get a minus 5. So what does this mean? This means that you get the potential start from initial bands to bend down to the intrinsic layer. So you get the phi f here. So phi surface equals to phi f, indicating the condition here. Okay, so when you apply the surface potential is bend down with negative phi f, that means you get the least charge accumulating along both surfaces, and you get the least capacitance because the slope or the carrier modulation is minor. So you get first we still have a modulation, but later times the slope degrade to almost 0 degree. However, later times when you further extended the potential, you further apply the inversion condition. That will make your surface potential below the intrinsic layer and put in weak inversion. Under weak inversions, you start to accumulate minority carrier again. So you get the capacity increase again. And the later times you can define the potential. We say the surface potential equals to 2 times of phi f. It means we get in strong inversion layer. So defining by minus 2 phi f. So you can think that start from the flat band condition. Flat means that you do not have any band bending in semiconductor. So there is no extra carrier accumulation along the surface. But when you apply either in positive or negative potential, in the positive potentials, you get the whole accumulation, and in the negative potentials, we try to first reach depletion region to minus phi f, but later on we get a strong inversion, so you get additional minority carrier accumulate, and this slope will equals to what will happen here, and it will be proportional to exponential q phi s, which is the surface potential over 2 kT, and this one should be larger than the acceptor layer. So for this one, we have the whole more p-type majority carrier hole, which is larger than the doping, the initial p-type doping. And then in the strong inversions, we talk about free electron, and this free electron should be larger than the initial hole type doping. So you can finish this plot. And of course, you can also consider if you have different charge or you have different type of doping polarity of semiconductor, we change the p-type doping to n-type doping. What will happen? We get a just opposite behavior. So you can think that if you get the positive one, first we deplete the electron, and then later on we have a strong inversion to accumulate the hole. And the other side, we just accumulate additional electrons in the n-type system. So you just inverse the curve for both p-type and n-type system. So that's what happened. Okay, so let us consider what is the charge distribution electric field and the electron potential for the inverse service, just like a p-n junction. So everything happens similar to p-n junction. The only difference is that what is the distribution in metal part. Okay, so we already talked similar behaviors in the metal to semiconductor junction, but the same thing happened here. So first, if you have the here's again, we use the p-type semiconductor as an example. The phi indicating the Fermi level is down below the intrinsic layer. If you apply the positive potential in which we want to accumulate more negative charge along the surface, it will first bend down the Fermi level to the intrinsic layer, to the Fermi level. So it will deplete the hole. And at that time, if you applied more phi S or more QV, you get this Fermi level even down to the intrinsic layer. Okay. Sorry, the Fermi level higher than the intrinsic layer. That means you get the electron accumulation. And the other last constant, of course, you can first plot the charge along the semiconductor. So for the charge along the semiconductor, you can first think that we get the negative charge because we get the the electron accumulation along the surface. But later on the other side, we get the positive charge of the metal surface. As we mentioned, there's no electric field in metal, so we can only have the charge shield along the metal surface. Okay, and then in between the metal and the charge, there's no charge trapping inside the insulator or outside layer. So you get nothing accumulating in between. And of course, you get additional behaviors or more charge accumulating in the surface, which is the exponential function. As we mentioned here, if you get the exponential decay for the potentials, you get the exponential growth of the free carrier. If you try to draw the corresponding electric field, you can clearly notice that the electric field is proportional from the semiconductor region. So from the semiconductor regions, we get the electric field accumulate with certain depleted widths. So we will start with here to the surface of the insulator. And then within the insulator, since there's no charge accumulation, so we will work like a constant or the same electric field in the dielectric material. And in the metal layers, as we previously mentioned, there should be no electric field. So there will be just a jump back to the zero potential. Okay, so while we have this potential distribution, you can consider that the condition, so the relationship between the charge and the electric field, based on Maxwell equation, we get a divergent E equals to rho over epsilon. So if you have the accumulating charge, it will be proportional, just like an integrated electric field along the semiconductor part. And how about the potential? What is the relationship between electric field and the potential? ED equals to the potential. So you can just integrate the electric field along axis. So when you integrated x, which is the linear relationship of the electric field, we get the polynomial behavior or second order polynomial. So we get the fires accumulating along here, just like what we showed, like a second order polynomial in the surface potential. And at that time, in the dielectric potentials, we just multiplied with a constant electric field as the distance. So we get a linear increasement in the electric field. And then later on in the metals, we get the same potential. And how about the relationship between the total potential and the applied field? It should be exactly the same. So you can think the applied potential externally equals to the accumulating potential from the depletion regions to the metal region. So the entire electric field multiplied with the distance of the electric field, we get the increasement. Okay. So based on this, we can try to look ahead. What is the accumulating data? So let us consider. So first we have a flat band. If you consider flat band, there will be no additional electric field. So if you draw this curve, the carriers will be exactly 0. So you can see there's no extra carrier accumulating along a surface. However, if you consider the other side, so for this one, so we get accumulations of EI, we get extra banding for the intrinsic layer. For the banding of the intrinsic layers, we get the by x, the surface potential by surface equals to -2 by x. Okay, so the definition between the intrinsic layer and the Fermi level indicates the by. Okay, so under the constant, you can draw the corresponding charge distribution, and this charge distribution give you first negative charge along the depletion region. So we get a negative charge here, and then later on you get a certain accumulation. So this one, which is the negative charge, and depending on what is the depletion region along x. And then we see the dielectric materials, we get the shell of the positive charge, which is positive charge here. And then the relationship between electric field and the charge will be divergent E equals to rho epsilon. So epsilon S is the dielectric permittivity of this material. And then this charge distribution is like the integrated of the electric field along x direction, and you assume that the two-dimensional shell will be the same constant. So under the constant, you can try to integrate the potential along x, which will be linearly increased. And here we get a positive one for the electric field. Okay. And then, of course, you can see if this electric field, if you are continue electric field or not. Okay, so the answer is means by the dielectric constant. If you have the same dielectric constant between insulator and the semiconductor, the electric field will be the same. However, the dielectric constant in traditional silicon and the oxide will be different. So typically in the sequence will be like 11.5, and then in dielectric oxide will be something like 2.2. Okay, so you get a large difference between these two. So what is the relationship? So typically it follow epsilon 1 E equals to epsilon 2 E2. Okay, so the higher the dielectric constant, you get less E. Okay, so at the boundary condition, you can consider the dielectric constant of oxide is less than secant dielectric constant. So what happened here is that you have this continuity of the electric field. One's here and the other one's here. That's based on our lecture. Okay. So once you get this electric field, you can try to integrate the form based on ED over the distance EX multiplied with D equals to potential X. Okay, so once we draw this line, we can try to integrate it first with the polynomial because X take the integration form is X squared over 2. So we get X squared along this line. And then times it is like a constant electric field. So a constant electric field multiplied with the distance between insulator, we get a linear condition. And then once in metals, we get a 0 electric field. So the total voltage applied from MIC system will be the voltage as we applied. Okay, so it is a really somewhat simple, but you can think that will be something we need to consider if you have 3 different layers connected with each other. So let me share the slide again. Okay. So if you further look through the process and talk about the equations we have, we can consider that the path drift along the metal, which we defined as the Qn. So we want to discuss more in details about what is the order, what is the depletion regions, like we defined in the semiconductor part, and how much it split the charge or depleted charge. And the Qn is the total metal or positive charge along the surface of metal, and it is balanced by the -1 in semiconductor. And for the metal one, the semiconductor one, it indicates by how much depleted charge. Or what is the depleted charge? So you can think if you go back to the previous slide, you first have the doping concentration in the p-type region. In the p-type regions, the doping concentration is Na. So how much charge in p-type region is how much depletion region multiplied with the charge density multiplied with the area. So you can go to the total charge is the QNA multiplies QW. So this one is like a surface charge density. And then we need to add additional negative charge in order to support the electron accumulation. So you need to get a negative charge in the as a whole as an electron. So the total charge, the positive charge along the surface equals to the depleted charge in a p-type region plus the total charge in the inversion layer. Okay. And the voltage applied indicating the voltage we pass in insulator and in the semiconductor region. So we have the phi s plus Vi. And then we can evaluate what is the corresponding capacitance in the dielectric material. The voltage across the insulators we indicating the electric field is a constant. We just look ahead the insulator or the voltage across insulator equals to the total charge times the um, distance between uh, the total charge accumulating the QSD over epsilon. So you can see that you can determine the QS, the surface charge divided by the capacitance we get for the unit area. Okay, so the capacitance defined by the insulator is epsilon multiplied with the area divided by the distance between the insulator. So you use this D, which is you divided by Ci. Qs over Ci is the voltage across insulator. So you take the Ci as the unit capacitance. And this unit capacitance is epsilon over D. So you get epsilon I here and D here. Okay. So the Ci here is the insulator capacitance per unit area, and the epsilon I is the permittivities of the insulator. And once you get this relationship, the next thing that we want to determine is the depletion region in semiconductor. So let us go back to the previous p-n junction. If you are familiar with the p-n junction, starting in mid-term, we get the depletion region, which is defined by 2 epsilon over Q, 1 over Na plus 1 over Nd multiplied with the additional building voltage. And this one can be simplified as we previously mentioned in the metal to semiconductor connection. If your metal, you can see the metal is infinite doping, so the Nd is much higher than the p-type system, so you can ignore the first term. So when you ignore the first term, you get 2 epsilon over Q, 1 over Na multiplied with the building potential. And how much it is the building potential determines how much surface potential we applied, right? So if you go back to the previous one, how much surface potential we have determines how much depletion region we get. Okay, just like the p-n junction. So when you determine it, you can clearly identify if you are working with different region, you get a different depletion region. If you are working with the depletion region, like you get the Fermi level exactly the same with the intrinsic layer. The surface potential equals to the Fermi 5. That means you get exactly zero accumulation along the surface. However, if you are working with stronger accumulation, stronger depletions or inversion layer, stronger inversion, that means it is 2 5. So you get additional potentials and a larger depletion region. So this depletion region determines how much area or how much voltage applied along the MI system. Okay, so let us try to look ahead for the entire operation voltage of the entire MI system. First, in comparing with the PN junction, it can be simplified as 2 epsilon Q over phi multiplied with phi s NA, take the square root. And for the magma depletion region, we consider the strong inversion. If you have the strong inversion, phi s equals to 2 phi f. Okay. So just insert 2FA into the phi term. If you look ahead for the phi f, it is defined by 2kT over Q log NA over NI. So you take this into the bracket, so you get log NA over NI 2, you get a 2 by 2 out of the square root, so you get a factor of 2 epsilon KT over Q squared, because we get a KT over Q based on the before the log NA over NI. So you get a comparison of this depletion region. If you get the larger voltage applied, you get additional depletion. And when we are working with strong inversions, the charge unit areas in the depletion regions can be then determined, because we get the depletion charge, which is the total accumulation between the depletion multiplied with the doping. So initially we need to deplete the hole, the majority hole. How much majority holes in semiconductor? We get the Q multiplied with the NA with the W max, which is the surface charge density. So you replace this W max with this function, you will know how much extra deplete charge we need to form the depletion region. And for the threshold voltage, if you want to build up the inversion layer, how much threshold voltage we need to apply? The first thing is that we need to apply additional to phi f, and also we need to consider how much charge we need to deplete for the depletion region. So that is the total voltage we need to supply. Okay, so imagine that the external voltage you applied may not be exactly the same with the fire, because you need to have a certain voltage to deplete the total charge in the insulator. So you need to overcome the voltage across the insulator. So not only the phi surface, but also the voltage potential in between the insulator. So that will be interesting to see. If you apply external voltage along MIC system, there will be two contributions. There will be partial potential across the dielectric layer, from the electric field along the dielectric layer. The other one is the surface potential across to the semiconductor surface and the insulator surface. So you need to consider both sides in order to get the total supplied potential. Okay, so when you apply this to potential, what is the unknown factor? So you need to know what is the doping concentration to determine how much depletion potential we get. And then we need to get the phi f, and this phi f can be determined by the scale of the NA over NI, take the log scale. And this phi f can be also determined by log NA or NI. So if you get the doping determines in the semiconductor, you can determine how much threshold voltage existing for the real state. And also you need to consider what is the dielectric constant of the insulator. So you add everything together. Okay, so it is the total electrostatic potentials we can supply within the entire structure. Okay. And then I want to first start